So far we've talked about how we can approximate the instantaneous rate of change, and by that we mean approximating the slope of the tangent to a curve. But is there a way we can do it more accurately? So let's consider the general case of finding the slope of a tangent drawn to the curve y equals f of x at the point where x equals a. And to do that, we're going to use limits. So we've just done a whole lot of calculating limits. Let's put it in context what it can actually help us with in this graph. So let's draw a tangent right here at x equals a. That's our tangent at x equals a. That point there is a. So the coordinates of that point right there are a, f of a. We've talked about function notation before. Let's also now consider another point right up here somewhere, so a bit further up the graph, and I'm actually not going to give that point coordinates because I'm just going to use sort of a generic coordinate x and f of x for that point. So say we called that point B, and if we were going to find the slope of the chord AB, we would just do f of x take f of a over x take a. For example, y2 take 1, y1 over x x2 take x1 is just a generalized form of that in terms of a. And that would tell you the slope of that chord, the slope of the chord joining the points a and b. Now we talked about this before. If we move b so it gets closer to a, the slope of that chord is going to approximate the slope of the tangent. So what we say is that the slope of the line, and we abbreviate it like this, let's show that again, it's f dash of a, so it's the slope of the line at a, the slope of the tangent at a is equal to the limit as x approaches a of f of x take f of a over x take a. And we use that formula when we want to find the slope, the value of the slope at a specific point. However, sometimes we don't want to just find the value of the slope at a specific point. If you think about a graph that looks like this, and say we want to find all these tangents on here, we want to find the value of the slope of all these tangents. Wouldn't it be great if there was a generalized equation for finding the slope of a tangent to this specific chord, to this specific curve? So that if we could have an equation that we know this is always going to be the general equation for the slope, so maybe it's something like y equals 2x plus 3, we know that's always going to be the general equation for the slope of that tangent, and all we have to do is when we get a specific point, we just substitute that in to our equation. And we can do that. That's called the derivative. So if we're thinking about that, we can draw another curve, a bit like the one we just drew, but we'll just set it up a little bit differently in order for us to be able to calculate that generalized equation. So if we've got our curve here, and we've got our 2 points here and here, we're going to call this one a and f of a, but this one, instead of calling it f of x and x of f of x, we're going to recognize that there's a distance between that point and this point. There's a horizontal distance, and I'm just going to call that length of that horizontal distance h. Okay, so therefore the coordinates of this point become a plus h, because that's going to be the x coordinate, and then in function notation the y coordinate is going to be f of a plus h. Now you'll notice as h gets smaller and smaller, or h approaches 0, the slope of the chord will become and approximate the slope of the tangent. So that's where our second equation for the general derivative, when we just want to find the general slope of the tangent, not at a specific point but just in general, we use the following formula. The slope of the tangent is calculated by doing the limit as h approaches 0 of f of x plus h take f of x over a. This is known as the general derivative function. So what you're calculating and what we're now doing is finding the derivative. By finding the derivative, we mean finding the equation for the slope of the curve at any point. So using these formulas, that is actually using limits to find the slope of the tangent, is known as using first principles. The result for part A, or the formula A, is known as the derivative at a point, and that's known as f dash of A. Alright, so where A is actually the x-coordinate of the point of contact. So that little bit, the derivative at a point A, that corresponds to this section up here. So that's the derivative at point A. In general, if we're doing the derivative in general, we use this formula. So depending on what the question asks, you'll use different formulas. If the question just asks you to find the derivative function, go straight to this formula. If it asks to find the value of the slope at a point, or the derivative at a point, you can use this function down here and then substitute in the point, but it's often easier to use this one over here, the first one we did. So, just quickly, just a bit of terminology you might come across. The derivative is known as the slope of the curve at a point where x equals a. In line with what we've just done, it's also known as the instantaneous rate of change of the function where x equals a. Or we can talk about it as the slope of the tangent to the curve with a point of contact at x equals a. Alrighty, let's do an example. So we're being asked to find by first principles this derivative at a specific point. So I'm therefore going to be using formula. I'm actually going to change this to y equals x squared. So just scrub that out and change it to an x squared. I'm going to use the formula that f dash of 2, because that x equals 2, is going to equal f of x take f of 2 over x take 2. What I get then is x squared take, instead of x I'm going to put 2, so take 2 squared over x take 2. Now I've missed something important there, and I hope you recognise that I've missed the limit sign, so I'm just going to scrub that out and make sure I put in the limit as x approaches 2. This is all about limits now, so that's going to equal the limit as x approaches 2. Now make sure you don't drop that limit sign off. Okay, don't just think, oh, I'll do my working out and put that in at the end. It's not correct unless you put the limit sign in. So you've got to put the limit as x approaches 2. Now, as you'll remember from the previous video, when we put in 2 to that, we'd get 0 down the bottom. So we have to do some factorising, and hopefully you can tell that the top line is actually difference between two squares. So that's going to, in fact, factorise quite easily and fall out quite nicely to form x plus 2 times x take 2 over x take 2. Then of course we just cancel that x take 2 term, and we'll get, when we substitute in x 2 for x, we'll get 2 plus 2, which equals 4. Alright, so that was a bit of a simpler one. Let's try this one, which is going to be a little trickier. We're again going to find by first principles the slope of the tangent at a specific point. So again, we know we're going to use that formula which has the slope of the tangent at a specific point. And so to use that formula, what we're going to do is go that the f dash of 3 is going to equal f of x first, so 2x squared, and of course remember to put your limit as x approaches 3. So limit as x approaches 3 of 2x squared take 3x plus 4 take, now we're going to do f of 3. We're just going to be careful here because everything's going to be taken away. Take 2 times 3 squared plus 3 times 3 plus 4, because take 4, sorry. And then we're going to divide that by x take 3. Now let's simplify that. So f dash of 3 is going to equal the limit as x approaches 3 of 2x squared take 3x plus 4. Now 3 squared is 9, so 2 times 9 is 18, so take 18 plus 9 take 4 over x take 3, which of course is going to simplify down to f dash of 3 equals the limit. If you can miss that middle step, that's fine. Of 2x squared, take 3x plus take 9 over x take 3. Now when we're doing this, we've just got to make sure, of course, that we get rid of that x take 3 in the bottom, because at the moment we can't use substitution. So to do that, we have to factorize the top, and it's really important that you're confident with factorization. So I'm just going to put x takes 3 on the top, because I know that's got to be one of the factors. And over here, I'm going to put 2x, because I know I've got to get 2x squared. And then negative 3 times by negative 3, positive 3 will give me a negative 9 term. And if you expanded that all through, that would be correctly factorized. So I've just got to cancel that, and then I'm going to substitute in my limit. So I do not get rid of the limit sign, really important. I don't get rid of the limit sign until I've actually done my substitution, which is going to give me the answer of 9. Okay, let's keep going. They get a little bit more complex here. In fact, these are probably some of the trickiest ones you have to do. So if you can do these, you'll be absolutely fine. We've got a denominator, but that's fine. We like denominators. So again, let's go with our formula. We've got going to go f dash of 4. So it hasn't specified x equals 4, but by putting f dash of 4, it means finding the slope or finding the derivative at x equals 4. So it's going to equal 3 over 2x take 1. Don't be put off by the fraction, just treat it like normal. Take 3 over 2 times 4 take 1, all over x take 4. Alright, now we've got an obvious thing there that we would like to get rid of, and that is the fractions. So first, let's just simplify that as much as we can. We get f dash of 4 equals 3 on 2x take 1, take 3 on 7 over x take 4. Now, if we simplify this and get the top line all onto one fraction, let's do that first. We need to get the lowest common denominator, so we're going to multiply the denominators together. And you probably remember this. In general, if you've got two fractions that you're either adding together or you're taking away from each other, what you do is that you multiply these two together, so a and d together, and then you multiply b and c together. And so that's where you get the AD plus or minus BC, depending on whether it's plus or minus, and then you multiply the bottom together. So that would give you 21. That's 3 times 7, being 21. Take 3 by 2x take 1, all over 7 outside of 2x take 1. And then again, all over x take 4. I'm going to run out of room here. So then f dash of 4, if we want to get rid of that fraction from the bottom, what we do is we actually multiply by it. So we multiply both the top and the bottom by that lowest common denominator. So if you see here what I mean by that, you do 21 take 3 bracket 2x take 1 over 7 times 2x take 1. I'm going to go on top of the other one, over x take 4. What we do is we times by 7 on 2x take 1 over 7 on 2x take 1. The reason we do that is we're just timesing by 1 over 1. And what we do when we get that is we can cancel. We can cancel that one with that one, and they go away. So then that one will simplify over here. Before I do that, I'm just going to note to something. I left out my limits again, so I'm just going to go back and change that. You change that on yours. All fixed, so that is going to be 21 take 3 bracket 2x take 1 all over x take 4 times 7 outside of 2x take 1. Now, really important thing here. Do not cancel those 2x take 1s, please. And also, never, never, never expand that denominator, because what we want to get rid of is the x take 4. Right? The x take 4 is our problem thing in here, and we still should have the limit as x approaches 4 in there. That should be in there. That's our problem, because when we substitute in, we're going to have issues. That's going to give you 0. So we're going to still have the limit as x approaches 4. We're going to expand the top. We get 21 take 6x plus 3 all over 7 bracket x take 4 bracket 2x take 1. It does not matter what order I choose to write that in. And then what we can do is we simplify the top line, because what you'll notice is that it will fall out very nicely. You'll get 24 take 6x all over 7 outside of x take 4 outside of 2x take 1, which of course factorizes if we take out the common factor of -6 to give you x take 4 over 7 bracket x take 4 outside of 2x take 1. Now we can cancel, get rid of that x take 4, and we get the limit as x approaches 4 of -6 over 7 times 2x take 1. Then we simply substitute in 4 and we get -6 over 49. That's our answer. Very long-winded process, looks scary, but in reality, if you just follow some key steps, you'll be absolutely fine with this. Write these down somewhere on your notes. So the first step, what was it? It was to get the top line to have the same denominator. So that's a with sign, with a common denominator. I'm just going to write out a series of steps here for you. So then we multiplied by the LCD over the LCD, then we simplified the top line, we didn't expand the bottom, we factorized the top, we cancelled the common factor, and then we substituted. What I'd like you to do is write those down and put arrows to where that actually occurred in that example. Now I'm not going to go on and do the next example, I think that's enough for now. You need to do some practice for this.